All right, problem number 25 in group theory. Is there a simple group of order 25? And we're going to do another Sylow theorem proof. Let G be a group of order 24, which is equal to 2 cubed times 3. Okay, by the Sylow theorems, the number of Sylow 2 subgroups is 1, or let's see, it has to be congruent to 1 mod 2 and it has to divide 3. So it could be 1 or 3. And the number of Sylow 3 subgroups is 1 or, okay, so it has to be congruent to 1 mod 3 and it has to divide 8. So it could be 1, can't be 2, can be 4, can't be 8. Okay, so it would be 1 and 4. Alright. Assume for the sake of contradiction that G is simple. Then the number of Sylow 2 subgroups is 3, and the number of Sylow 3 subgroups is 4. Okay. By the Sylow theorems for conjugation, we have that G acts by conjugation on its Sylow subgroups, on its Sylow 3 subgroups, giving us the homomorphism phi from G to S4. Also, these can't be 1 because if it were 1, then that would be a normal subgroup, which would contradict that they're simple. Okay. Moving forward, remark that the kernel of phi is a normal subgroup of G. Hence, since G is simple, the kernel phi is trivial. If it were non-trivial, then it would be a non-trivial normal subgroup, which would contradict the simple fact. Okay. By the first isomorphism theorem, we have that G is isomorphic to the image of G, which is a subgroup of S4. Considering orders, the order of G is equal to 24, and the order of S4 is 4 factorial, which is also 24. Just put the order symbol. Okay, so these have equal orders, and this is isomorphic to something that's a subgroup of it, hence they have to be equal. Hence, G is equal to S4. Otherwise, it would be a subgroup of S4 with the same order of S4, which the only subgroup of S4 that has the same order as S4 is S4. Okay, consider orders. Okay. This is a contradiction since S4 has a normal subgroup, namely the Klein 4 group. Therefore, G cannot be simple. Therefore, there are no groups of order 24.